Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 57. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with influence of delta connected tertiary winding on three-phase autotransformer. Three-phase autotransformer, while connected and put in service with the extra high voltage power transmission system, then that autotransformer is obviously been exposed to various voltage and current stresses. The winding part that would also have to undergo certain thermal and mechanical stresses as due to the resultant effect of short circuit currents. It is important to note that any sort of single phase to ground short circuit, while occurs in the network with an isolated neutral point, then that may instigate to trigger off the unfaulted phase voltages significantly higher than operating values, that is operating voltages rather. Such occurrences may eventually lead to internal winding insulation failure, causing a major operational disruption. See the diagram, autotransformer with delta tertiary winding and the zero sequence circuit. The presence of delta connected tertiary winding would have to interact with the zero sequence impedance of the autotransformer. As of the figure 180, delta connected tertiary winding is commonly used to provide a low impedance path for third harmonic currents. Delta connected tertiary winding would also have the ability to restrict considerable extent of current and voltage imbalances caused by asymmetrical loading effect. Normally, delta connected tertiary winding is designed for at least one-third of the rated power and having the lowest rated voltage. It is so designed that its winding must have the ability to withstand the effects of a short circuit fault across the external terminals as well as those due to earth faults on the main windings. Technical specification for autotransformer design and engineering. Autotransformer, though it does not provide any electrical isolation to load from mains and is more prone to faults, but still it is advantageous to use over the conventional one up to a voltage ratio of about 3:1. It is as because of smaller in overall size, lighter in weight, and cheaper in cost than that of the same capacity dual winding transformer. It has also to possess lower leakage reactance, higher efficiency, good power quality, and less copper requirements. However, inability to provide electrical isolation between the input and output, which means that if there is a fault in the output circuit, then it would have to affect the input circuit as well, and that could be dangerous. Such disadvantage is even more prominent, but at the present context, where the power system that would have the specialty in designing with continuous escalation of voltage level as per with the increase of transmission capacity, autotransformers are widely used because of their large capacity, low loss, and low cost. Autotransformers would be a good option for applications where high efficiency and compact size be the prime requirement and where electrical isolation is not a critical requirement. Again, I repeat, autotransformers would be a good option for applications where high efficiency and compact size be the prime requirement and where electrical isolation is not a critical requirement. So, it is what to note that auto transformer may not be the suitable option for applications where voltage regulation would have been the critical requirement or where electrical isolation would be the prime necessity. In most of the cases, large autotransformers that are usually made to be perfectly suitable for parallel operation with the existing transformer as available in the station. To make it suitable for parallel operation, there would have some important parameters that are to be taken care of during designing and engineering of that particular autotransformer. Most vital one. See the diagram, vector representation rather. Primary, secondary, tertiary, and see the representation. It is important to note that the design parameters such as the percentage impedance, vector group, on-load tap changer connections with tapping range, etc. of the specified autotransformer would have to be mentioned or would have to be rather matched with that of the existing transformer. Autotransformer must be so designed that it would have to be capable of being continuously operated at its rated MVA without showing any abnormality at any tapping position with voltage variation of plus minus 10% corresponding to the voltage of the tapping. Requisite autotransformer must be so designed that it is being capable to operate at the overloaded conditions with the norms as prescribed in the standard IEC 60076-7. All the autotransformers, even are the most efficient and are capable to use for bidirectional flow of rated power, but would have to generate heat while in use. Based on the maximum ambient temperature of 50 degrees centigrade, the tank hotspot temperature would never be allowed to exceed 130 degrees centigrade. Stage-wise cooling system, which has come into operation by preset contacts of winding temperature indicator, would thus to protect against damage from heat and may also enhance its KVA rating. The size and design of an oil-filled autotransformer is mainly influenced by the loading with cyclic variations and its supplemental cooling systems. As per guidelines of IEEE standard C57.91 2011 and IEC 60076-7 2018, type of cooling systems that are to be categorized through cooling classes under various operating temperatures and loading conditions on the process of autotransformer thermal aging. Now see the chart. Cooling class, IEEE designation, cooling method are to be adopted. Oil natural, air natural, that is ONAN. Oil immersed, self-cooled, that is heat transfer of oil by natural air convection. Number two, oil natural, air forced, ONAF, forced air circulation using fans and blowers. Oil forced, air forced, OAF, AF. Oil immersed, forced oil cooled using pumps. Non-directed flow with forced air cooler. Oil forced directed flow, air forced, that is ODAF. Oil immersed, forced oil cooled, directed flow with forced air cooler. Oil natural, water forced, ONWF. Cooled by surrounding oil, forced water circulation using through heat exchangers. Oil forced non-directed flow, water forced, OFWF. Forced oil cooled, non-directed flow and water circulation using oil to water heat exchanges. Oil forced directed flow, water force, that is ODWF. Forced oil cooled directed flow and water circulation using oil to water heat exchangers. Autotransformer, while in auto changeover sequence from natural cooling class to stage-wise forced cooling class, that would have to come in operation through the actuation of preset contacts of winding temperature indicator. To mitigate the heat dissipation problem, radiator banks that are to be fitted with the autotransformer main tank must have to maintain certain standard design criteria. It is rather to be recommended that out of 4 radiator banks as fitted with the main tank, 3 banks should have the capability to dissipate total heat as generated inside the tank at continuous maximum rating operation, and one radiator bank usually, though, will be in service, but that would have been deployed as standby. Hence, each of the radiator banks is thus to be designed for dissipating 33.3% of the total heat loss at continuous maximum rating independently. Each radiator banks would have to design in such a way that it has to dissipate 33.3% of the total heat loss at continuous maximum rating independently. From the statistical review, it has been exhibited that there are several evidence of catastrophic failures of very large forced oil cooled power transformers where the electrostatic charging incidence of insulating fluid would have been the probable cause. As due to the incidence of continued co- uh, 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 continual frictional interference between the insulating fluid and the solid interfacing part, then there may have the possibility to generate the static electrification. Again, I repeat, as due to the incidence of continual frictional interference between the insulating fluid and the solid interfacing part, then there may have the possibility to generate the static electrification. However, the ultimate process of electric charge separation that would have to occur when the oil flows at the inner surface of the cooling ducts in the narrow gaps between transformer barriers and around the paper insulation of transformer high voltage windings, HV windings. The electrostatic charging process and the amount of charge to generate both would have been characterized by the direct influence of the chemical structure and electrical parameters of the insulating fluid as used. The electrostatic charging tendency of oil that can be determined by evaluating the conditional factors such as resistivity, dielectric dissipation factor, interfacial tension, oil flow rate, temperature, water content, and cellulose particles within the fluid. All are the vital factors. Resistivity, dielectric dissipation factor, interfacial tension, oil flow rate, temperature, water content, and cellulose particles within the fluid. As a customer, it is well understood that under all operating conditions, which includes all sorts of prevailing oil circulation systems, the oil flow speed is thus to be so designed that the autotransformer must have been kept free from any electrostatic charging tendency. Based on the perception that faults in power transformers often occur after a oil forced cooling system needs to be switched on. And that is why well adjusted oil flow speed would have been anticipated, and it is generally not exceeding 1 meter per second. However, total unit is comprised of main transformer along with all its accessories, including bushings, built-in cities, etc. During designing, it is the prime objective to have an intensive attention on selection of all the associated attachments connected with the subject autotransformer. So this has become composite unit, and at the operational stage, the unit must have to withstand all sorts of thermal and mechanical stress as initiated due to sudden effect of any external short circuit to earth or short circuits at the terminals of any winding for at least a period of 2 seconds. In accordance with IEC 60076-7, the short circuit level that should be conformed as corresponds to the high voltage and intermediate voltage system to which autotransformer would have been connected. Technically, it has been exhibited that higher be the flux density in core and yoke of a transformer, which leads to higher iron losses, and that directly affects its overall efficiency. So, selection of ferromagnetic material that would have been an important issue on designing the core of a transformer. It is rather recommended that under 10% continuous overvoltage conditions, the maximum flux density in any part of the core and yoke would never be exceeded 1.9 Tesla at all tap positions. Most important. The tertiary winding, which would act as to supply low tension LT auxiliary power, must have to design with the basic criteria of withstanding mechanical and thermal stresses due to dead short circuit on its terminals. While designing the active component of autotransformers, it is much necessary to have a prior selection of better grade of raw materials like ferromagnetic core material of CRGO composition, current carrying copper conductors, insulation material. In order to achieve long life of the transformer with least maintenance, there may have a strict quality control with the best possible process engineering that should be carried out so as to meet all requirement stipulated in the technical specification as framed by the purchaser. The core formation that has to construct with the stacking of individually insulated thin laminations inside the high-grade, non-aging, cold-rolled, high permeability, grain-oriented silicon steel material. The core magnetic circuit should be so designed that in no way may cause any possibility of local heating. The temperature of any part of the core or its support structure in contact with insulating oil shall never be exceeded 120 degrees centigrade under normal operating condition and 130 degrees centigrade under most extreme operating conditions. We are well aware that for a good quality of transformer oil that has the flash point as high as 140 degrees centigrade, transformer oil would have to act as a key role in the insulation and cooling system of any form of transformers. To counter the possibility of hot spot at the winding part, the coil assembly and insulating spacers would have been so arranged where a continuous free flow circulation of oil that can be ensured. Very important. For constructing medium, for constructing medium to ultra high power transformer winding, it is necessary to select the conductor which has to offer better cooling efficiency, increased mechanical and electrical strength, and at the same time cost effective. As of the improved winding capabilities, there may have to use continuously transposed conductor, that is CTC, continuously transposed conductor for the specialized design and fabrication of windings. For detailed discussion, see link of the power transformer part 6, https /YouTube YouTube slash KZM XTS C9PAE. Basically, in order to reduce eddy current and to equalize the distribution of currents and temperature along the winding, the conductor as used that would therefore be usually of type transposed at sufficient intervals. For applications in oil field transformers, these conductors are thus to be insulated in combination of polyvinyl acetal based enamel with high density paper insulation of having high mechanical strength. Autotransformer, as it is being facilitated to have some complicated interconnections for making the voltage and current from one level to another level, with the basic perception of maintaining a constant output irrespective of the input to a certain level. Constant monitoring and control of on-load tap changer mechanism would have been a custom for a mandatory requirement to meet the smart grid standards. Proper remote functionality of OLTC mechanism for achieving the constant voltage regulation as corresponds to system requirement. The OLTC controller that must be designed with the IEDs, that is intelligent electronic devices. Intelligent electronic devices rather actually to be framed with the perception of a composite unit of microprocessor based controllers, and that has to function with corresponds to some prerequisite parameters as provided. Designing of IEDs with their related components would have been the most precise engineering activities, as because the technology basically provides fast and selective protection, monitoring, and comprehensive control of all types of interconnecting transformers. IED, intelligent electronic devices, would also to cater all sorts of tasks, including specific routine engineering management, communication engineering process, disturbance record management, service management, etc. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.